So let's do one more problem, and then I'll talk about competitive equilibrium. Okay. So suppose let's now consider the same feasible set. Okay, feasible set is x1, x2, g in R3 plus such that x1 plus x2 plus g is equal to 10. Okay, and let's assume quasi-linear utility functions. Okay, so suppose u1 x1 g is equal to, what is it? Let's say x1 plus 2 root g. Okay, and let's say u2 x2 g is also x2 plus 2 root g. Okay, so yeah, let's just take symmetric so that we don't have to. Okay, again we can draw the set of all feasible allocations: origin of 1, origin of 2, also the origin of the firm. Okay, this is x1, x2, in this direction it is g. Okay, okay, so now this is 10, this is also 10. So how will you figure out Pareto efficient allocations in this case? Okay, well, again you have to do something with the individual 2, because for individual 1 it's completely normal. Okay, this is x1, this is g, so you can just draw it the way you draw. So for individual 2 you have to convert it into, you know, using feasibility, you just have to convert it into you know, something that you can handle, which is a function of x1 and g. Okay, so u2 10 minus x1 minus g, okay, comma g. Okay, which is what? Well, you can just replace this x2 by 10 minus x1 minus g plus 2 root g. Okay, now what we are going to do is we are just going to figure out the slope of the indifference curves. Okay, to see what's going on. Okay, so let me just you know, figure out the slope of the indifference curve of individual 1. We have already done this you know, several times. Okay, so let's just do that quickly. Okay, so if you want to find the absolute value of slope, you can just straight away do this: del u1 by del x1 upon del u1 by del g. Okay, and when you're going to do this, this will be 1 and this will be 1 upon root g, so 1 upon 1 by root g, and that's going to be root g. Okay, so this is the absolute value of the slope. The actual slope is actually minus root g. Okay, this is the absolute value of the slope, and if you're going to plot it, you know, you can see that as g goes to 0, okay, the IC gets flat. Okay, it's just very flat. Okay, it's get flatter and flatter as g goes to 0. So basically, you know, you're going to get indifference curves like this. Okay, is that fine? Okay, you can see that as g goes to 0, this curve you know, gets you know, when it hits the axis, it's just going to have slope 0. Okay, at that point. Okay, is that clear? Okay, and they'll have intercepts. Okay, they'll have intercepts because as we have seen that, you know, if you're going to put 0, if you're going to put x1 equal to 0, you can figure out what g it is, and if you're going to put g equal to 0, you're going to figure out what x1 it is. Okay, they are not asymptotic. Okay, so now let's do the same thing for individual 2. Okay, so for individual 2, let me just you know, to figure out the slope, let me just set u bar equal to, so this is the equation of the indifference curve. Okay, and let's take the, you know, just differentiate this with respect to x1. Okay, so obviously when you are on on an indifference curve, this utility is constant. So if you want to differentiate this with respect to x1, this will be 0. This will be -1. This will be minus dg by dx1, okay, and then plus 1 upon root g into dg by dx1, right? Yes? Yes or no? Is everybody getting this clear? Okay. Now what I'm going to do is I'm just going to figure out the slope. Okay. So dg by dx1, I'll just take that common, okay, from this term, okay, and I'm going to get what? 1 upon root g minus 1, okay, and I'm going to take it to the other side, so I'm going to get this equals to 1, right? So dg by dx1 is what? Dg by dx1 is, let's take this to the denominator, 1 by root g minus 1, okay, and I'm going to get what? 1 minus root g in the denominator and root g in the numerator. Are you all getting this? Please note that this is not the absolute value of the slope, okay, this is the actual slope, okay. So this tells you that when g is less than 1, okay, then ic is upward sloping, okay, and when g is greater than 1, then this term is negative, so the ic is downward sloping, okay, and when g is approaching 1, the curve is going to get vertical, almost vertical, because the slope is this particular thing is going to approach infinity. Is that okay? As g gets close to 1, yes or no? Well, g gets close to 1 from the left, then this will be infinity. As g gets close to 1 from the right, this will be negative, but the key thing is that it's just vertical, okay, so that's all that matters, okay. So basically what we have is, you have something like this, you have 1 here, okay, okay. So you can just analyze this, and then you'll just get that it's just going to have this shape, okay. It's upward sloping for g less than 1, okay, it's upward sloping for g less than 1, and then it's downward sloping above 1, okay. So at 1 it is vertical. Is this clear? Okay, now clearly, you can see that below 1, okay, there is no efficient allocation, because this ic is downward sloping, this ic upward sloping, so obviously there is a region here where you can improve the satisfaction level of both. For example, if you look at this point, you can go here and you can improve the satisfaction level of both. So no point below 1, okay, is Pareto efficient. Is that clear? Okay, so basically whatever efficient point are there are going to be above this one, okay. You can also check at the corners, by the way, this is upward sloping, this is downward sloping, so again you can see that if you move here you can improve the satisfaction level of both, okay. So because this is on a higher IC for both this guy and this guy, okay. So below 1 not possible, okay, no efficient allocation below 1, okay, and by symmetry you can also rule out this one, okay. So so we need to check in this region now, okay. So for the interior, okay, interior means that you can just ignore the boundaries for the time being, okay. For the interior, what do you think is the requirement for efficiency? What do you think will be the requirement for efficiency? Exactly, it will be this tangency, right? Okay, so all that you have to do is you just have to equate the slope of this IC with the slope of this IC to get efficiency. So here you just have to be a little careful, don't equate absolute value of the slope of this one to the actual value of the slope of this one, okay. You have to equate, if you are equating the absolute value, because this is downward sloping, this is downward sloping, so if you are equating the absolute value, just make sure that both are absolute values, and if you are equating the actual value slope, then make sure both are actual value of the slopes. Okay, so let's just equate. So this is the absolute value of the slope. Okay, so root g is equal to, and when g is greater than 1, okay, what is the absolute value of this one? It is root g upon root g minus 1, right? Yes, because when g is greater than 1, the absolute value of this is root g upon root g minus 1. Okay, so now we can equate them and figure out what g is, along the points which are efficient inside the triangle. Okay, so what are we going to get? G minus, okay, so root g cancel, and we are going to get root g minus 1 equal to 1. So g equal to 4, right? So basically this gives you all the Pareto efficient allocations inside the triangle, okay, which is going to lie on this line. Okay, so let's write this. Okay, so all these are Pareto efficient. Okay, are there other Pareto efficient allocations? What do you think? Are there any other Pareto efficient allocations? Okay, let's check on the boundaries now. Okay, so that's all that we need to check. What about this point, for example? Is this Pareto efficient? How will you check it? We are just going to compare the slopes at this point, right? Compare the slope of the IC of individual 1 with IC of individual 2 and figure out whether the IC of individual 2 go from below it or above it. Okay, that's all that you need to do. Okay, so G is greater than 4, right? So notice that this and this, okay, if we just compare these two, okay, let's see when is this bigger than this. Okay, fine. So let's just solve this. Okay, again we can do the same thing. Okay, and we are going to get what? Well, root g is root g minus 1 is greater than 1, which gives you g greater than 4. So notice that g greater than 4 is equivalent to this. G greater than 4 is equivalent to this. Okay, what does this mean? This means that when g is greater than 4, then individual 1's IC, okay, is steeper because its absolute value of the slope is bigger, okay, than individual 2's IC. Okay, so it's steeper than individual 2's IC. So individual 2's IC is going to be flatter, right? Like this. Okay, so if it is, this is steeper, this is flatter, this is how the situation will look. Now what can you say about a point like this? Do you think this is better than this one? Yes or no? Okay, better means in terms of Pareto comparison. Yes, right? Okay, so you can see that if you move from this point to this point, you can improve the satisfaction level of both. So clearly this is not Pareto efficient. Okay, this is not Pareto efficient. Okay, now you can do the same check over here. Okay, and of course by symmetry you can also ignore these points. Okay, because if these are not Pareto efficient, it's just the same thing from individual 2's perspective. Okay, and these are not going to be Pareto efficient. You can do the same check over here. Okay, so if you do the check over here, you will find that the IC of individual 2 will look like this. So we just have to check whether IC of individual 1 looks like this or like this. Okay, so you can actually redo this calculation. Okay, so if you redo this calculation, you will find that when G is less than 4, this term is less than this term. Okay, what that means is that individual 1's IC is actually flatter than individual 2's IC. So basically the situation will look like this. Is that clear to everyone? Okay, so that means this point is Pareto efficient. Okay, so what you're going to get is that these points are Pareto efficient. Okay, these points are Pareto efficient. Okay, and these points are Pareto efficient. Okay, so now we can just write the set of all efficient allocations. X1, X2, G in the feasible set such that, what about these points? What is true about these points? G is 4, right? Union X1, X2, G in the feasible set such that, and what about these points? What is true about these points? G is between 1 and 4, okay, and either x1 is 0, okay, or x2 is 0, okay. Okay, so I'll just rewrite this, okay, for x2 equal to 0. Okay, by the way, let me tell you one way in which you can actually figure out at least a subset of Pareto efficient allocations by maximizing the sum of the utilities. Okay, so if you do this problem, okay, so let's say maximize the sum of the utilities. So what is the sum of the utilities? X1 plus x2 plus 4 root g. If you maximize this with respect to x1, x2, g, and subject to the feasibility, which is x1 plus x2 plus g is equal to 10, okay, and of course the non-negativity constraint applies. So if you want to do this particular problem, you will find that you will get all these points. You'll not get the corner points, okay, you'll only get these points. Okay, so maximizing sum of utilities will give you the set of efficient allocations, but it will only give you a subset. Okay, I mean, it's possible that it might give you the entire set, okay, but it may not give you the entire set all the time. Okay, so like in this case, if you maximize the sum of the utilities, you will only get these points. Okay, so in these problems, the problems that we have seen so far, it will give you the subset. Okay, but of course, I mean, you can construct examples where it can give you the entire set, but it will definitely give you a subset. Okay, that's for sure. Okay, because when the sum of the utilities is maximized subject to the feasibility, then of course any point that maximizes the sum of the utilities, any feasible allocation that maximizes the sum of the utilities has to be Pareto efficient. Okay, the reason is because if such an allocation is not Pareto efficient, and there is a feasible way in which you can improve the satisfaction level of one of them without reducing the satisfaction level of the other, then you can also improve the sum of the utilities, right? Yes or no? So therefore, any feasible allocation that maximizes the sum of the utilities will also be Pareto efficient, but the converse may not be true. Okay, and the converse may not be true. You can see the example here. For example, you can see this point. Okay, this is a point where x1 is what? X1 is 0, g is 1, and x2 is what? X2 is 9, right? Okay, this is a point you can easily check it doesn't maximize the sum. Okay, but it is Pareto efficient. Okay, you can quickly check. Okay, you can just maybe compare this point and this point. The sum will be higher at this point. Okay, so let's do that quick check. At 4, what is this at this point? Okay, at this point x1 is 0. Okay, x2 is 6. So this is 6 plus 4 times square root of 4, which is 6 plus 4 times 2, which is 14, right? Okay, and at 1, which is also Pareto efficient. Okay, if you do this sum, you are going to get 0 plus 9 plus 4, which is 13. Okay, so in fact all these allocations will give you the same sum. Okay, but these allocations, as you move down, the sum will fall. Okay, but still they are Pareto efficient. Okay, it doesn't mean they are not Pareto efficient. Okay, similarly these are by symmetry Pareto efficient as well. Is that clear to everyone? Okay, now why is this Pareto efficient? You can just, of course, the picture is telling you that it is Pareto efficient, but you can also do that by this logic that if you just look at this particular point. Okay, now if you just look at individual 2, individual 1 doesn't have any amount of private good left. Okay, will individual 2 individually want to contribute more to the public good, if he is the only one who has to contribute? Okay, and if you just do the derivative here, okay, and figure out the MRS of just individual 2 with respect to public good, you're going to get what? Root g. Okay, and you want to compare it with what? Well, because if he's going to give out 1 unit of private good, he's going to get back 1 unit of public good in return, so he has to compare it with 1, right? So notice that at this point he doesn't want to do any contribution because G is 1. Okay, if G is 1, he doesn't want to contribute further unless the other person also contributes. Make sense? So if he's the only one who has to contribute, he's not going to contribute anymore. Is that clear to everyone? Okay, so yeah, I mean that's basically the idea why this is the range of set of all efficient allocations. Similarly, we have set of all efficient allocations here. Okay, now let's talk about competitive equilibrium. Okay, is that fine?